This laser calibration interferometer works because monochromatic laser light forms consistent wave peaks. The clever bit here is recombining split beams to measure movement. When a single laser beam splits into two perpendicular paths, one reflects off a fixed reference mirror. The second beam travels to a target mirror mounted on a precision sliding carriage. Recombining these two reflected beams produces optical interference, generating alternating bright and dark fringe bands across a photodetector as the moving carriage glides down the rail. By continuously counting these passing optical fringes, the system measures physical travel against the known wavelength of red laser light, creating an ultra-precise non-contact ruler. However, relying solely on raw optical fringe counts assumes that the speed and wavelength of laser light remain completely stationary inside open laboratory air. In reality, ambient atmospheric changes in room temperature, barometric pressure, and relative humidity continuously alter the air's refractive index along the optical track. A tiny air temperature shift of just 1 degree Celsius stretches the physical optical wavelength enough to create significant micromillimeter errors over long measurement spans. If these subtle atmospheric shifts go uncorrected, uncompensated wave counts accumulate silent optical distortion across the full length of a long calibration bench. Without continuous environmental monitoring, counting raw light waves alone fails to provide absolute length traceability required for national measurement standardizations. Metrologists resolve this atmospheric distortion by surrounding the calibration bench with a dense network of high-precision ambient environmental sensors. Multiple calibrated sensors continuously track ambient temperature, atmospheric pressure, and humidity levels along the entire length of the optical beam corridor every second. An automated central processing unit feeds these live environmental parameters directly into the modified Edlin equation to calculate the exact optical wavelength in real time. Simultaneously, surface contact temperature sensors mounted directly on the granite structure monitor physical thermal expansion occurring within the mechanical bed and mounting fixtures. By dynamically recalculating the true laser wavelength against live sensor readings, the system maintains nanometer-level measurement precision despite shifting laboratory room conditions. This continuous real-time mathematical correction transforms open-air laser light into an incredibly stable optical measuring stick capable of extreme scientific repeatability. The bigger problem was applying this sub-micron optical precision to flexible commercial steel tape measures spanning up to 60 full meters in length. Flexible steel tape ribbons bend, stretch under tension, and sag under gravity, making direct non-contact optical measurement exceptionally challenging over long continuous distances.
Relying on human technicians looking through magnifying optical microscopes causes severe visual fatigue, subjective line alignment, and unavoidable parallax errors across thousands of marks. Furthermore, the heavy steel tape ribbon must be held under exact standardized mechanical tension without inducing microslippage across its support surface. Verifying every printed graduation mark automatically along an entire long tape required combining laser interferometry with high-speed computer vision and precise motion control. The complete system mounts the long steel tape along a flat, temperature-stabilized bed, clamping one end while applying standardized deadweight tension to the other. A heavy motorized carriage supported on frictionless air bearings glides smoothly along precision granite guide rails parallel to the stretched steel measuring ribbon. A frequency-stabilized helium-neon laser projects a collimated red beam parallel to the travel path, inside a protective enclosure that shields the light from air currents. An optical beam splitter divides the laser beam into two parts, directing one path into a fixed reference arm and sending the other downstream. The measurement beam strikes a retroreflective corner cube prism fixed directly to the moving carriage, reflecting back along its original path to recombine at the splitter. As the air-bearing carriage glides down the track, the returning light wave phase shifts relative to the reference beam, producing dynamic light interference patterns. High-speed photodetectors convert these optical interference cycles into quadrature electrical signals, allowing the system to track displacement direction and count fringes continuously. Rigidly attached next to the optical prism on the carriage, a high-resolution digital microscope camera continuously captures close-up images of the passing tape surface. Real-time image processing software analyzes contrast profiles across each mark, calculating the precise mathematical center of every graduation line on the tape. The exact instant the computer vision software identifies a mark center, it triggers a hardware latching pulse that instantly freezes the interferometer's current fringe count. The system logs this measured optical displacement against the nominal line location, building a high-resolution map of micromillimeter positioning deviations. Contact temperature sensors continuously measure the steel tape's temperature, applying thermal expansion equations to normalize all measured lengths to 20 degrees Celsius. This automated dual detection workflow checks hundreds of calibration graduation lines per minute with complete mathematical objectivity and zero human visual fatigue. Every physical mark across the entire multimeter steel ribbon is tied directly and traceably to the fundamental international system definition of the meter.
The gathered calibration dataset yields an exhaustive official report, revealing microscale manufacturing periodicities, pitch drift, and overall dimensional accuracy. By uniting optical wave interference with automated line-finding camera technology, metrology institutes provide bulletproof physical calibration for industrial measuring tools. Every everyday tape measure validated through the system carries physical graduations calibrated directly against the invariant speed of light in a vacuum. Keep the explanation observational. Do not encourage improvised laser exposure, staring into beams, or constructing a tensioned calibration bench without suitable training and laser safety controls. Understanding this harmonious combination of laser physics and precision mechanics reveals how modern industry maintains absolute confidence in physical dimensions. From large infrastructure projects to high-precision aerospace manufacturing, world-class engineering depends fundamentally on this invisible link to atomic light standards. Through the constant, meticulous counting of microscopic light cycles, metrology guarantees that a millimeter marked on a tape remains exact anywhere on Earth.